Hi, I'm Jamie with the Chegg Tutors. Today I want to talk to you about a pretty simple probability distribution called a discrete uniform distribution. Now let's take apart each of those words. Discrete distribution, meaning that the random variable will have a finite number of outcomes. This is different than, say, a uniform distribution on the interval 0, 1, where there are an infinite number of possible outcomes, any decimal between 0 and 1. Uniform means that each of the, say, n possibilities has an equal chance of occurring. Since the probabilities of all the possible outcomes have to add up to 1, this means that each event, each number, has a 1 over n chance of occurring. Now, an example of this, a pretty simple example, would be a fair die. In this case, there are 6 possible outcomes, and the probability of each of those outcomes is 1/6. Now, we have to be careful. The distribution for a biased die, where the probabilities would not be equal of getting each number, is still a discrete distribution. There's a finite number of outcomes, but it is not uniform. Let's calculate a few things about this discrete uniform distribution. Here I'm assuming that the distribution is just the numbers 1 to capital N, the n being the number of outcomes. You could also say that the distribution is from, say, A to B, where A and B are integers. But to make it easier, let's just consider the case which you can map any uniform distribution to, where we have n possible outcomes, and each of those outcomes is represented by a number from 1 to n. In this case, the expected value of x, the random variable, is simply, as we know, the sum of the probability of a certain outcome I times the value of that outcome. In this case, the outcomes are just integers, and the probability is equal. It's 1 over n for each outcome. So we have the sum of 1 over n times I, where I goes from 1 to n. Now we can pull out that 1 over n since it's constant in each of the terms, and we end up with 1 over n times the sum from I equals 1 to n of I, just the integer. I'm not going to go through the derivation, but we know that the sum of the numbers from 1 to n is simply n times n plus 1 over 2. Since we divided all of that by 1 over n in the beginning, we end up with the expected value, or the mean, of this distribution as n plus 1 over 2. This kind of makes sense. We want something that's close to n over 2, plus or minus some correction for an odd or even number. Because if each thing is equally likely, and you have the numbers from 1 to n, approximately you're going to get half that are below n over 2, half that are above n over 2. So our mean is n plus 1 over 2, which we can think about intuitively, but also just in terms of the math. The variance gets a little more complicated, and honestly, I need you to just believe me on the formula for the sum of squares here. So the variance, the definition is the expected value of x squared, the random variable x squared, minus the expected value of x, all of that squared. Now we recognize the expected value of x is just that mean of the random variable, which we calculated last time. It's n plus 1 over 2. So in this case, whatever the variance is, it's going to be the expected value of x squared. We'll need to calculate that, minus n plus 1 squared over 4, which is just the mean that we got previously squared. This is where you have to kind of take it on faith. You can look up a proof or look up the formula, but the formula for the sum from I equals 1 to n of I squared, that is the sum of the squares of the first n numbers, n integers, is simply n times n plus 1 times 2n plus 1 over 6. Again, we're dividing that by that constant n that we see outside the sum, and that means that the expected value of x squared is n plus 1 times 2n plus 1 over 6. If we do a little more algebra, which I'm not going to bother showing you, subtracting the n plus 1 squared over 4, we get that the variance is n squared minus 1 over 12. There are various other things that you could calculate, using this distribution, but those are the main ones you want to know. You also want to know that this distribution is useful for a lot of combinatorics problems and a lot of problems where you're playing a game, picking marbles, doing all sorts of things where the outcomes are unbiased. They're equally likely, but you have a finite number of possible outcomes. That's it, and thanks for watching.